early 1944, Dayton, Ohio. A brisk winter morning hung over the airfield as a lone P-51B Mustang rested on the tarmac, its polished fuselage catching the first rays of sunlight. Inside the cockpit, the test pilot's hand hovered over the throttle. Outside, engineers huddled around instruments, exchanging quiet glances. Today was different. Today wasn't about incremental improvements or the minor tweaks every engineer celebrates. Today, the Mustang was about to push beyond everything the Allies or anyone had ever achieved in fighter performance. With a steady hand, the pilot pushed past standard war emergency power. The engine roared to life, vibrations coursing through the airframe as the experimental fuel, known simply as Grade 150, poured into the combustion chambers. Purple-dyed gasoline, a chemical marvel born from countless hours of laboratory tests and refinery experiments, ignited the engine like a bolt of energy. The airspeed indicator crept past thresholds that had been considered untouchable. At 25,000 feet, the Mustang tore through the thin air at 448 miles per hour, faster than any Allied fighter before it. On the ground, the engineer's eyes widened. This wasn't a marginal gain. It was a revolution. The implications of this fuel were staggering. Allied pilots flying what they thought was an ordinary P-51 suddenly had the power to outpace every German fighter in the sky. The Luftwaffe, confident in their Messerschmitt Bf-109Gs and Focke-Wulf FW-190s, had no idea what was coming. Their assumptions about American aircraft performance, forged through countless encounters over France and England, were about to be shattered by a chemical advantage they could never match. The story of this advantage didn't begin in a war room or with daring aerial tactics. It began in peacetime labs and refineries, where American and British chemists tinkered with molecules, understanding that octane ratings measured not just fuel quality, but raw combat potential. Higher compression, higher power, faster climb rates, these weren't just technical details. They were keys to controlling the skies. By the time the Mustang descended from its test run, the world above Europe was about to change. And it would happen silently in the purple streak of aviation, gasoline coursing through engines, designed to push limits, but never this far. Engines' roar had barely faded when the significance of Grade 150 fuel became clear to those watching from the ground. It wasn't just about speed, it was about changing the rules of aerial combat. Every turn, every climb, every dive was suddenly governed by a hidden variable: chemistry. While German engineers struggled with synthetic fuels derived from coal, struggling to coax a meager 91-octane performance from their Messerschmitts and Focke-Wulfs, the Allies had unlocked something extraordinary: German B4 fuel. Rated at 91 octane on the lean mixture scale, left Luftwaffe pilots with no margin for error. Their premium C3 fuel, though better, barely approached the capabilities of Allied 130-grade fuel. Meanwhile, American refineries were producing aviation gasoline with a performance number of 150. That number wasn't just a statistic, it was a weapon. On standard 130-grade fuel, a P-51 Mustang could already reach 437 mph at 25,000 feet. Impressive by any standard. But with Grade 150, the same aircraft, flown by the same pilot, could exceed 448 mm/s, pulling ahead in ways that German pilots could not counter. The German frontline fighters, the Bf-109G and the FW-190A, had been top performers, capable of 400 and 408 mph respectively at altitude. Against Mustangs on 130-grade fuel, German pilots had at least some hope of maneuvering on equal footing. Against Grade 150 Mustangs, they faced a fundamentally different challenge. They were simply slower, and no amount of skill, clever tactics, or daring could bridge that performance gap. The secret wasn't in the airframe or engine design alone. It was in the chemistry of the fuel. Octane ratings measured how much a fuel-air mixture could be compressed before it detonated spontaneously. A higher number meant more power per combustion cycle. The science seemed straightforward, but the engineering required to produce this fuel at industrial scale was complex, involving precise blending of tetraethyl lead and aromatic hydrocarbons to prevent knocking, all while maintaining energy content suitable for high-performance engines. Even before the war reached full scale, American refineries were already experimenting. In 1940, standard aviation gasoline hovered around 87 octane, adequate for trainers and commercial planes, but insufficient for high-altitude combat. The British, facing the Luftwaffe's superior numbers, had collaborated with American oil companies to develop 100-octane fuel, which became crucial during the Battle of Britain. Spitfires and Hurricanes surged with 30-40 mph additional speed at altitude, and climb rates increased dramatically. It was the first hint that fuel could change the tide of aerial warfare. By 1943, the Allies had moved further, producing 130-grade fuel, which powered Merlins, Allisons, and massive Pratt & Whitney radials. Guided by aviation fuel advocate General James Doolittle, production scaled rapidly across 17 Allied refineries, thanks to the catalytic cracking process refined by Eugene Houdry. The Americans weren't just keeping up, they were creating an industrial edge Germany could not match. And then came Grade 150. Purple. Potent and precise, it promised performance that would leave the Luftwaffe scrambling, forced to confront an enemy who could fly faster, climb higher, and strike with power that seemed almost supernatural. The story of this fuel, its creation, and its battlefield impact would unfold in ways German planners could never predict. The history of high-octane aviation fuel traces back to pre-war innovations. Chemists realized that increasing fuel's resistance to detonation could unleash higher power in aircraft engines. By compressing the air-fuel mixture more aggressively without risking uncontrolled explosions, engines produced significantly more horsepower. The British pioneered 100-octane fuel in collaboration with American oil companies. Early tests proved immediate performance gains in Spitfires and Hurricanes. Climb rates improved by up to 1,000 ft per minute, and high-altitude speed advantages forced the Luftwaffe to rethink engagements. The U.S., leveraging vast oil reserves and industrial capacity, moved rapidly to develop 130-grade fuel, which powered everything from the P-51 Mustang to the P-47 Thunderbolt. By 1943, millions of gallons were produced monthly, enough to support bomber escorts and fighter operations over Europe. Industrial capacity, combined with careful chemical engineering, created a level of air power that Germany could not match. The Luftwaffe, reliant on synthetic coal-based fuels, faced production bottlenecks. Even the best German fuel, C3 grade, could not consistently match the performance of Allied 130 or 150 grade fuel. When the first test batches of 150 grade fuel were evaluated, engineers noticed immediate gains. P-51 Mustangs achieved higher manifold pressures without detonation. Power output jumped from 1,190 horsepower to over 1,600. Speed and climb improvements were achieved without any modifications to the airframe, purely through chemical advantage. By early 1944, experimental runs at Dayton revealed what engineers had long suspected. Grade 150 fuel could push existing fighters beyond their original design limits. Test pilots reported higher climb rates, better acceleration, and sustained performance at altitudes that would have previously strained engines to the breaking point. The P-51B Mustang, already a formidable aircraft, became something closer to a Predator, fast, responsive, and virtually untouchable by any German fighter. Engineers meticulously monitored manifold pressures, temperatures, and RPM, realizing that the new fuel allowed engines to operate at previously impossible levels without catastrophic detonation. This wasn't just about speed, it was a psychological edge. Pilots could push the throttle forward with confidence, knowing the engine wouldn't self-destruct under the strain. The Luftwaffe had no concept of this chemical advantage. German pilots relied on standard B4 and C3 fuels, often encountering knock, pre-ignition, and power limitations at high altitude. Meanwhile, Allied Mustangs and Spitfires could sustain high power settings longer, climb faster, and escape unfavorable engagements with ease. The war in the skies was about to be fundamentally transformed. Creating Grade 150 fuel wasn't just a laboratory achievement, it was an industrial triumph. American refineries, guided by Doolittle and engineers like Eugene Houdry, scaled production to millions of gallons monthly, supporting not just isolated units but entire fighter wings. Every gallon required chemical additives, quality testing, and precise blending. Purple dye was added to prevent mistakes, a visual cue for ground crews and pilots. By contrast, Germany's synthetic fuel production remained constrained by coal availability, complex chemical processes, and bombing raids. Even their best fuel, C3, was available only in limited quantities. German fighter units often had to ration fuel, limiting operational flexibility and placing pilots in a constant state of caution. Allied fuel superiority meant something far more significant than speed. It allowed the entire air strategy to be executed with confidence. Escort missions could use maximum power when needed, patrols could be extended, and intercepts of fast-moving targets became feasible. Fuel was no longer just a commodity, it was a weapon. Understanding grade 150 fuel requires understanding octane ratings and performance numbers. Octane measures detonation resistance. When a piston compresses an air-fuel mixture, temperature and pressure rise. If fuel ignites prematurely, it creates destructive shock waves. High-octane fuels resist this, allowing more compression, higher manifold pressures, and greater horsepower. Grade 150 was more than a number. It represented a 50% improvement in compression tolerance over pure isooctane at rich mixture settings. It required precise blends of tetraethyl lead and aromatic hydrocarbons, engineered to prevent knocking while delivering maximum energy. This chemical mastery translated directly into the cockpit. P-51 pilots could climb faster, dive harder, and sustain high-speed maneuvers that German pilots couldn't match. For every dogfight, fuel became the silent arbiter of victory. May 1944 marked the first operational deliveries of grade 150 fuel to England. Distribution was controlled carefully, with priority given to fighter squadrons tasked with high-speed interception missions, particularly those engaging the new German V-1 flying bombs. These missiles traveled around 400 mph at low altitudes, making standard intercepts difficult. Mustangs running 150 grade fuel could reliably match or exceed the V-1's speed. Pilots learned innovative techniques, like tipping a V-1's wing with their own wingtips to destabilize it, a maneuver only possible because the aircraft could maintain high-speed control and precise positioning. The first documented successful interception occurred on June 18, 1944, setting the stage for a wave of operational successes. The Normandy invasion in June 1944 provided the first large-scale test of grade 150 fuel in combat. 8th Air Force P-51s, now equipped with the superior fuel, flew combat air patrols and escorted bombers with unprecedented efficiency. German pilots reported encounters with Mustangs performing far beyond expected limits. Luftwaffe intelligence initially dismissed these reports, assuming pilot error or exaggeration. But multiple engagements confirmed the truth. Allied fighters were faster, more agile, and more powerful, capable of dictating the terms of every engagement. By late summer 1944, the Luftwaffe faced an uncomfortable truth. Reports from the front lines painted a consistent and unsettling picture. Allied fighters were performing beyond anything previously experienced. German pilots who had engaged Mustangs since 1943 were stunned. Even seasoned aces, veterans of the Eastern Front and countless aerial engagements, noted a disturbing pattern. Allied aircraft seemed to possess virtually unlimited energy reserves. They could climb rapidly, accelerate out of seemingly impossible maneuvers, and maintain high speed at altitudes that would have previously strained or even destroyed an engine. What made this phenomenon so disorienting was its invisibility. The P-51 Mustangs, Spitfires, and Tempests looked the same. There were no new airframes, no secret weapons, no radical aerodynamic modifications. Yet their performance envelope had expanded dramatically, allowing American and British pilots to dictate engagements. Dogfights that had once been contests of positioning and tactical cunning now felt lopsided. German pilots found themselves reacting defensively, often forced to disengage or risk catastrophic losses. The Luftwaffe's intelligence services eventually obtained samples of the mysterious purple fuel. Laboratory analysis revealed the hard truth. This was grade 150 aviation gasoline, a chemical formulation beyond the capabilities of Germany's coal-based synthetic fuel program. Whereas German C3 fuel approached octane performance numbers equivalent to early Allied grades, it was inconsistent, scarce, and vulnerable to Allied bombing raids. The Allies, in contrast, had achieved a fuel capable of sustaining extreme boost pressures without detonation, enabling maximum engine output and unmatched speed. The operational consequences for the Luftwaffe were immediate and severe. High-performance sorties became risky gambles. Units were forced to ration their limited supplies, curtail training flights, and adopt conservative operational policies. Even veteran pilots were acutely aware of the growing disparity. Aircraft that previously could be outmaneuvered or outrun now accelerated away before effective engagement could begin. The psychological impact was profound. Pilots felt outnumbered, outfueled, and outpaced, a combination that eroded morale and confidence. Every engagement became a test of restraint. German pilots had to calculate fuel reserves meticulously, often breaking off attacks not because they were losing in combat, but because they lacked sufficient fuel to return safely. The invisible superiority of grade 150 fuel imposed an additional layer of strategic pressure, one that no amount of tactical skill could fully compensate for. For the first time, the Luftwaffe had to acknowledge that Allied dominance in the air was not just a matter of pilot skill, numbers, or aircraft design. It was a technological and industrial triumph, a chemical advantage that German forces could neither replicate nor counter effectively. The realization set in slowly but inevitably. The air war over Europe was tipping decisively in favor of the Allies. And the purple liquid flowing through Mustang and Spitfire fuel tanks was a weapon as lethal as any gun or bomb. By late 1944, the cumulative effect of this realization was evident in both strategy and morale. Aggressive sorties were increasingly avoided. Luftwaffe formations operated cautiously, aware that any engagement could result in disproportionate losses. Veterans who had once taken pride in their superiority now faced the sobering reality that even the best German fighters could no longer dictate the terms of aerial combat. The chemical and industrial might of the Allies, invisible yet omnipresent, had fundamentally altered the strategic landscape. The shock was not merely technical, it was psychological. German pilots, trained for years to expect parity or advantage, now confronted an opponent whose performance seemed limitless, sustained by fuel chemistry, industrial scale, and meticulous planning. In the end, it was a lesson that transcended aerodynamics and engineering. War could be won not just by weapons or skill, but by the unseen. Carefully engineered advantages that transformed ordinary aircraft into extraordinary tools of dominance. Reports from summer 1944 onward showed dramatic improvements in Allied fighter effectiveness. Escort missions saw losses drop from 3 to 6% per mission to under 2% after widespread grade 150 implementation. P-51 groups claimed thousands of enemy aircraft destroyed, often before German fighters could effectively respond. The combination of pilot skill, aircraft design, and chemical advantage created decisive superiority. Luftwaffe formations, previously confident in their ability to intercept bombers, found themselves outmaneuvered and outgunned, not by numbers alone, but by the unseen power in purple gasoline coursing through the Mustang's engines. At the heart of the Mustang's dramatic transformation was the Packard-built Merlin engine, a masterclass in engineering that married British design brilliance with American manufacturing precision. Originally, the Merlin had been designed to deliver reliable high-altitude performance within strict thermal, bearing, and detonation limits. Engineers had painstakingly balanced every aspect of its operation: manifold pressure, cylinder temperatures, bearing tolerances, and compression ratios, to create an engine that could endure combat conditions without catastrophic failure. But the introduction of grade 150 fuel unlocked a latent potential that designers had always known existed but could never exploit fully. With the new fuel, the Merlin could sustain 75 inches of manifold pressure, far beyond its previous war emergency limits of roughly 67 inches. This increase in manifold pressure translated directly into horsepower surges of 250 HP, pushing P-51B and early D variants into performance realms previously considered impossible for piston engine fighters. Flight tests confirmed what pilots soon realized in combat. The Mustang had become something more than a plane. It had become a predator in the sky. Acceleration at altitude was instantaneous, climb rates soared, and energy retention during maneuvers was unprecedented. A pilot could choose the engagement entirely on their own terms, initiate combat, disengage at will, or pursue enemy fighters relentlessly, knowing the engine's performance would not falter. The balance of power in the air had shifted subtly but decisively. German pilots, by contrast, were constrained by fuel limitations and engine tolerances. Messerschmitts and Focke-Wulfs could reach their design specifications only under optimal conditions, often struggling to maintain high boost settings without risk of detonation or mechanical failure. Every high-speed attack had to be measured, every climb carefully calculated. Allied pilots no longer faced these limitations. With grade 150 fuel feeding the Packard Merlin, the Mustang became a chemically enhanced instrument of dominance, capable of sustaining extreme performance without penalty. The implications extended beyond raw numbers. In combat, the combination of fuel chemistry and engine design created a new tactical reality. Dogfights were no longer a simple contest of skill versus skill. They were increasingly a contest of energy management, where Allied pilots enjoyed a hidden reserve of power and speed. This advantage allowed them to dictate the pace of engagements, forcing German pilots to react defensively or abandon the fight entirely. Moreover, the surge in performance did not compromise engine longevity as severely as one might expect. While maintenance crews noted increased cylinder wear and spark plug fouling due to the high tetraethyl lead content in grade 150 fuel, the engines themselves could withstand repeated maximum power operations without catastrophic failure. Ground crews adapted, adjusting maintenance schedules and inspection intervals. And the payoff was a fighter whose true capabilities were revealed only in combat. The Packard Merlin Surge, powered by grade 150 fuel, epitomized the fusion of engineering foresight, industrial capability, and chemical innovation. On the battlefield, the Mustang was no longer merely a well-designed airframe. It was a weapon system whose performance was amplified by science itself, an advantage invisible to the enemy until it was unleashed in the sky. Allied pilots quickly learned to exploit this power fully, executing high-speed intercepts, extended climbs, and rapid disengagements with confidence. In essence, the Merlin engine running on grade 150 fuel transformed the P-51 Mustang from an already formidable fighter into a plane that redefined air combat, introducing a combination of speed, climb, and sustained power that German pilots had never anticipated. Every throttle advance became a tactical decision backed by the certainty that the engine and fuel would deliver, turning ordinary dogfights into engagements dominated by chemistry and engineering as much as skill. Grade 150 fuel didn't just increase speed, it changed strategy. Faster Mustangs allowed 8th Air Force fighters to dictate engagements, choosing when to strike and when to disengage. Escort missions became safer. Bomber formations could fly deeper into Germany with reduced losses. German fighters, once capable of slashing attacks and retreating, now faced Mustangs that could accelerate away, climb above, or turn sharply with minimal risk. Every tactical option narrowed for Luftwaffe pilots. High-octane power came with trade-offs. Tetraethyl lead, the key anti-knock additive, was toxic and corrosive, requiring careful handling by ground crews. Spark plugs fouled more quickly, cylinders wore faster, and maintenance schedules had to adapt. Despite the increased workload, the gains were undeniable. The Mustang's combat effectiveness soared, and engineers and mechanics innovated solutions to handle the maintenance demands. Industrial and logistical coordination became as critical as chemical engineering itself. Transitioning to grade 150 fuel required updated operating procedures. Pilots had to manage manifold pressure and throttle settings carefully, balancing maximum power with fuel consumption. Escort missions already pushed the Mustang's range to the limit. Using the full potential of 150-grade fuel demanded precise judgment. Training programs adapted quickly. Pilots learned when to push the throttle, when to cruise, and how to maximize power without risking engine failure. This combination of chemical advantage and human skill created a formidable synergy in combat. By June 1944, Allied Mustang squadrons were poised to make full operational use of grade 150 fuel, and the results were immediate and staggering. As the P-51s took to the skies over Normandy, the advantages engineered in laboratories and refineries became vividly apparent in combat. For years, Allied pilots had contended with German fighters capable of matching or exceeding their aircraft in speed and climb. But now, with the new fuel, the energy envelope of the Mustang had expanded dramatically, giving pilots unprecedented control over the engagement. Frontline reports detailed a pattern that repeated across multiple squadrons. German fighters could no longer outrun or outclimb the P-51s. The previously reliable tactic of hit-and-run or diving attacks no longer guaranteed survival for Luftwaffe pilots. Allied pilots could climb, accelerate, and reposition at will, effectively dictating the tempo of combat. Dogfights that had once been tense and uncertain were now controllable and increasingly one-sided. One of the most striking applications of this newfound capability was encountering the V-1 flying bombs, the so-called buzz bombs that terrorized London with their high speeds and low-altitude flight. Intercepting these missiles had always been a challenge. Traditional fighters struggled to match their speed, often engaging too late or unable to maneuver close enough for an effective attack. But Mustangs running grade 150 fuel had sufficient acceleration and climb performance to reach the V-1s quickly, enabling pilots to engage them at ideal angles. Combat reports from June 1944 described a range of techniques. Some pilots tipped the wings of the V-1s with their own wingtips, a precise maneuver requiring the fighter to approach within mere inches of the missile. The airflow would destabilize the V-1, causing it to veer off course and crash harmlessly away from populated areas. Others used direct fire, leveraging the Mustang's high speed and agility to maintain the correct firing solution despite the V-1's velocity. These successes were not isolated. They became a routine demonstration of how the new fuel extended operational capabilities beyond previously imaginable limits. Pilots quickly adapted to the fuel's potential. By carefully managing throttle and boost, they could maintain maximum performance for extended periods, crucial for long-range escort missions over Normandy or deep strikes into occupied territory. The combination of speed, climb rate, and energy retention allowed Mustang squadrons to control engagements, intercept fast-moving targets, and disengage at will, a level of tactical flexibility that German pilots had never faced. The psychological impact on both sides was profound. Allied pilots, confident in their chemically enhanced machines, flew with a new sense of daring and initiative. They knew that their aircraft could accelerate beyond German interceptors, climb above attacks, and maintain combat energy in situations that previously would have been considered too risky. Conversely, German pilots, now confronting these enhanced Mustangs for the first time, were forced into a defensive posture, realizing that their traditional tactics were insufficient. The operational debut of grade 150 fuel during the Normandy campaign was thus more than a technical success. It represented a strategic shift. Aircraft that had once required careful management of engine power and altitude now had performance reserves that enabled decisive action, and pilots wielded this advantage with increasing effectiveness. The combination of chemical engineering, precise manufacturing, and tactical expertise had transformed the Mustang into a weapon system capable of shaping the battlefield, protecting Allied bombers, and neutralizing threats such as the V-1 flying bombs with unprecedented efficiency. In these early operational successes, it became clear that grade 150 fuel was not just an improvement, it was a game-changer, redefining what was possible in air combat and signaling a new era of Allied air superiority over Europe. The Luftwaffe faced an unprecedented dilemma. Their numbers were still substantial, but the performance gap created by grade 150 fuel meant German pilots were chronically outmatched in every engagement. Veteran aces reported feeling frustrated and demoralized. Even experienced pilots who had survived years of Eastern Front combat were shocked by the speed, climb, and power of the Mustangs. Fuel, an invisible element, had shifted the balance of power in the sky. The operational impact of grade 150 fuel became visible in strategic bombing campaigns. Loss rates for bomber formations dropped sharply, as P-51s could now neutralize Luftwaffe attacks before they reached the bombers. Escort missions became more aggressive, with pilots actively seeking engagements rather than merely defending. By late 1944, German air resistance had weakened, allowing Allied bombers to strike deep into Germany with increasing efficiency. The skies over Europe were increasingly dominated by Mustangs fueled by chemical advantage. German intelligence initially dismissed reports of superior American fighter performance as exaggeration. Yet captured fuel samples revealed the truth. Grade 150 fuel had performance numbers Germany could not replicate. Even the late-war C3 fuel, Germany's best, was inconsistent and produced in limited quantities. Allied bombing of synthetic fuel plants further constrained output. German pilots now faced a scenario where industrial and chemical limitations dictated tactical choices. Historical accounts from the summer and fall of 1944 provide vivid examples of how grade 150 fuel transformed air combat. Among the most striking was the engagement of Lieutenant Hollis Bud Nallin, flying his P-51D Mustang, nicknamed Hell's Bells, over Eastern Europe. Nallin's mission was a routine escort for a bomber formation. But what unfolded that day would illustrate the revolutionary edge provided by chemically enhanced aviation fuel. Spotting a Messerschmitt Bf-109 attempting to intercept the bombers, Nallin engaged. With grade 150 fuel coursing through the Packard Merlin engine, his Mustang could accelerate and climb at rates previously thought impossible. In a matter of seconds, he closed the distance to the German fighter, positioning himself for a decisive attack. Utilizing the Mustang's newfound speed, climb performance, and energy retention, Nallin unleashed a burst of fire that severely damaged the Bf-109's cooling system. The German aircraft, now crippled, was forced into a desperate belly landing near enemy lines. Nallin, meanwhile, disengaged without sustaining damage or excessive risk, a feat that would have been far more dangerous with standard fuel. This was not an isolated incident. Across multiple fighter groups, similar engagements occurred repeatedly, each reinforcing the growing reputation of Allied fighters as nearly untouchable in certain regimes of speed and altitude. German pilots, trained to anticipate traditional performance limitations of Allied aircraft, found themselves consistently outpaced and outclimbed. Even experienced aces were confronted with a startling reality. The Mustangs they had flown against in previous years now performed as if they had been fundamentally redesigned, their engines capable of sustaining extreme power settings without the catastrophic risk of detonation. Chemical superiority became tactically decisive. Engagement reports showed German pilots surviving encounters not because they outmaneuvered Allied fighters, but because Allied pilots chose not to press the attack, fully aware that additional bursts of maximum power could completely overwhelm their opponents. In many cases, German aircraft were damaged, forced to abort missions, or crash-landed, while Allied Mustangs returned safely with minimal losses. The effect was psychological as well as operational. German pilots began to report encounters in which American fighters seemed to possess energy reserves beyond comprehension, able to accelerate away or climb without apparent effort. The Luftwaffe, already strained by fuel shortages and pilot attrition, faced a new kind of frustration. The enemy's performance advantage was not just due to superior tactics or numbers, but a fundamental chemical and engineering edge. Historical records detail numerous squadrons adopting similar tactics, using the Mustang's extra power from grade 150 fuel to dictate engagement altitude, close rapidly, inflict damage, and disengage at will. These engagements underscore the reality that air superiority in 1944 was increasingly dependent on factors invisible to the naked eye: octane ratings, manifold pressures, and chemical properties of fuel that German pilots could neither replicate nor counter effectively. In essence, every successful engagement highlighted a single, transformative factor. Grade 150 fuel had shifted the balance of combat in favor of the Allies. Pilots were no longer merely relying on skill and training. They wielded a weapon of chemistry and engineering that made previously daring maneuvers safer, extended operational envelopes, and produced outcomes that directly influenced the trajectory of the air war over Europe. The Mustang, already a superb airframe, had become an instrument of calculated dominance, where every sortie was backed not just by pilot expertise, but by the invisible, formidable power of superior fuel. And with each engagement, the Luftwaffe's tactical options narrowed further, revealing the decisive role of chemical innovation in modern aerial warfare. By the end of 1944, the strategic implications of Grade 150 fuel were undeniable. Allied fighters could operate multiple sorties daily, maintain standing patrols, and sustain aggressive operations without fuel limitations. German fighters, constrained by scarcity and rationing, were limited to cautious engagements. Operational flexibility and industrial capacity became intertwined with battlefield performance. The result? Decisive air superiority for the Allies, paving the way for strategic victories on the ground and in the air. Grade 150 fuel was no longer just a chemical marvel. It was a force multiplier that shaped the outcome of the war. By early 1945, the full impact of Grade 150 fuel was undeniable. American and British pilots flying P-51 Mustangs and Spitfires had gained not just speed, but a psychological and tactical edge over the Luftwaffe. The aircraft themselves had not changed, yet the chemical composition of their fuel had transformed them into weapons that could outperform any German counterpart. Every mission flew with the assurance that acceleration, climb rate, and sustained power were now largely dictated by superior fuel chemistry. For German pilots, the scenario was increasingly desperate. Experienced aces who had survived years of combat over Europe and the Eastern Front now faced an enemy whose aircraft could climb faster, accelerate away at will, and sustain maximum power without engine risk. Their tactical options narrowed. Even when German squadrons outnumbered Allied escorts, they could no longer rely solely on maneuver or sheer speed. Grade 150 fuel had effectively tilted the air war in favor of the Allies, independent of pilot skill or tactics. The chemistry behind this success was subtle but profound. Octane ratings determined detonation resistance. Performance numbers quantified how much higher compression could be sustained safely. With Grade 150, the Mustang's Merlin engine could withstand 50% more compression at rich mixture settings than the pure isoctane standard. This translated directly into horsepower, which pilots could convert into speed, climb, and maneuverability, all without touching the airframe or engines themselves. The strategic value extended beyond individual encounters. Fighter groups could patrol longer, escort bombers further, and intercept enemy aircraft faster than previously possible. German commanders, constrained by fuel shortages and the limitations of C3 grade synthetic fuel, could not mount effective counter-strategies. The industrial advantage of the Allies became a tactical advantage in the sky, one that Germany could not mitigate. The dramatic increase in performance came with challenges. Tetraethyl lead, the core anti-knock additive, was highly toxic, necessitating careful handling and specialized protective equipment for ground crews. Spark plugs fouled more frequently, cylinder wear accelerated, and engines required more regular inspections. Yet Allied maintenance teams adapted rapidly, shortening replacement intervals and adjusting overhaul schedules to keep up with the new fuel's demands. For pilots, operational adaptation was equally critical. Using Grade 150 required a balance between maximum power and fuel conservation. The new fuel could deliver unmatched speed, but at the cost of significantly higher consumption. Escort missions deep into Germany demanded careful throttle management and precise timing for maneuvers. pilots trained rigorously, learning to exploit the fuel's power without compromising range. The combination of meticulous maintenance, careful operational planning, and chemical advantage meant that Allied forces could deploy aircraft at their true potential, a capability the Luftwaffe could neither replicate nor counter. This was a revolution born not from technology alone, but from the seamless integration of chemistry, engineering, logistics, and tactical doctrine. By mid-1944, combat reports confirmed the dramatic effects of Grade 150. 8th Air Force squadrons reported encounters where Mustangs could dictate terms of engagement, pursuing or evading German fighters at will. Dogfights, which had previously relied on pilot reflexes and positioning, now hinged on raw energy reserves provided by fuel chemistry. One notable engagement involved Lieutenant Hollis Bud Nayland of the 357th Fighter Group. Flying his P-51D Hell's Bells, Nayland engaged a Messerschmitt Bf-109 over Eastern Europe. With Grade 150, his aircraft accelerated rapidly, closed the distance, and inflicted significant damage, while German attempts to escape were futile. Nayland returned with minimal fuel consumption and intact aircraft, demonstrating how the fuel itself created an operational advantage independent of pilot skill alone. These encounters multiplied across multiple theaters. German pilots, facing a consistent pattern of faster, more capable Allied aircraft, began to adjust tactics defensively. Rushed interceptions, evasive maneuvers, and cautious engagements became common, signaling a psychological edge in addition to the chemical one. By late 1944, Germany faced severe strategic constraints. Fuel shortages, bombing of synthetic plants, and the cumulative effects of Grade 150 enhanced Allied fighters forced severe operational limitations. Even elite units received rationed fuel, cutting training and combat readiness. Young pilots entered operational units with minimal experience, while seasoned aces faced insurmountable performance gaps. The disparity was stark. Allied pilots could fly multiple sorties daily, operating at maximum power when necessary. German pilots, by contrast, were limited in both frequency and intensity of combat missions. Every engagement became a calculated risk, not from potential losses alone, but from insufficient fuel to complete missions or return to base. The chemical edge of Grade 150 fuel had translated directly into a strategic imbalance. Operational data confirms the effect. Between June and December 1944, following widespread adoption of Grade 150 fuel, loss rates for bomber formations dropped below 2% per mission. Victory claims skyrocketed. American P-51 groups across all theaters claimed thousands of enemy aircraft destroyed, representing not just losses for the Luftwaffe, but the systematic elimination of experienced pilots. These statistics underscore the connection between industrial chemistry and battlefield outcomes. Allied fuel production and quality exceeded Germany's total output across all grades, enabling continuous operations, higher sortie rates, and sustained pressure. The purple liquid coursing through fuel lines was as decisive as bombs or bullets in shaping aerial supremacy. Grade 150 fuel was not limited to American units. British squadrons flying Spitfires, Tempests, and Mustangs benefited similarly. RAF pilots reported identical improvements in speed, climb, and intercept capability. Tempest squadrons, tasked with V-1 interceptions, achieved remarkable results. Between June and September 1944, RAF 150 Wing Tempest destroyed hundreds of flying bombs, often using innovative wingtip techniques. Directly enabled by superior fuel performance, Allied coordination ensured optimized allocation of Grade 150 fuel, maximizing the impact across both strategic and tactical operations. Squadrons equipped with the fuel became force multipliers, reshaping the air war over Europe. Beyond physical performance, Grade 150 fuel produced a psychological advantage. German pilots knew they faced aircraft faster and more powerful than anything they had encountered before. Reports of Mustangs accelerating away mid-dogfight, climbing beyond reach, or sustaining high-speed maneuvers demoralized even the most seasoned Luftwaffe units. Confidence shifted to Allied pilots. They could engage with assurance, pursue targets aggressively, and operate at the fuel's limits without fear of mechanical failure. This shift in morale and tactical confidence became a force multiplier alongside the chemical edge itself. Allied production of Grade 150 fuel represented an extraordinary feat of industrial engineering. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons, with total Allied consumption exceeding 200 million gallons. Each gallon required complex refining, blending, quality control, transportation, and secure storage across multiple theaters. This industrial scale allowed the Allies to sustain continuous air operations while Germany struggled. The ability to produce, distribute, and utilize Grade 150 fuel efficiently magnified its tactical impact, turning chemical superiority into operational dominance. By 1945, the Luftwaffe had effectively ceased to exist as a coherent force. Jet fighters like the Me-262 appeared too late and in insufficient numbers, handicapped by fuel shortages and inexperienced pilots. Allied fighters, powered by Grade 150, flew hundreds of thousands of sorties, achieving decisive air supremacy. German pilots faced limited sorties, rationed fuel, and a relentless opponent. The skies over Europe were no longer contested. The combination of chemical advantage, industrial capacity, and pilot skill made Allied dominance absolute. On May 8, 1945, Germany surrendered. The air war over Europe had ended decisively. While many factors contributed, pilot training, numerical superiority, aircraft design, the chemical edge provided by Grade 150 fuel was a critical, often overlooked factor. The Mustang, unchanged in design from early 1944 to 1945, became a faster, more capable fighter purely due to fuel chemistry. The purple gasoline turned ordinary aircraft into lethal, decisive weapons influencing every engagement, dictating strategy and shaping the outcome of the war. Grade 150 fuel exemplified the integration of science, industry, and strategy. It was a reminder that victory in modern warfare depended not only on courage or tactics, but also on the unseen, meticulously engineered advantages that allowed one side to outproduce, out-innovate, and ultimately outlast the enemy.